A piston is a cylindrical part that reciprocates inside a car engine cylinder, needed to change gas pressure into mechanical work, or vice versa, reciprocating motion into a change in pressure. Thus, it transmits to the connecting rod the force arising from the gas pressure and ensures the flow of all cycles of the working cycle. It looks like an inverted glass and consists of a bottom, a head, a guide part skirt. Gasoline engines use flat bottom pistons due to ease of manufacture and less heat during operation, although on modern cars they make special recesses for the valves, so that when the timing belt breaks, the pistons and valves do not meet and do not entail a serious repair. The bottom of the diesel piston is made with a recess, which depends on the degree of mixture formation and the location of the valves and injectors. With this shape of the bottom, the air is better mixed with the fuel entering the cylinder. The piston is exposed to high temperatures and pressures. It moves at high speed inside the cylinder, initially for automobile engines. They were cast from cast iron. With the development of technology, aluminum began to be used because gave advantages, an increase in speed and power, less stress on parts, better heat transfer. The power of modern engines has increased. The temperature and pressure in the cylinders of engines, especially diesel ones, became such that aluminum approached the tensile strength. Therefore, modern motors are equipped with steel pistons that confidently withstand increased loads. They are lighter than aluminum due to thinner walls and lower compression height, i.e., distance from the bottom to the axis of the aluminum pin, and the steel pistons are not cast, but prefabricated, reducing the vertical dimensions of the piston. With the same cylinder block makes it possible to lengthen the connecting rods. This will reduce lateral loads in the piston-cylinder pair, which will positively affect fuel consumption and engine life, or, without changing the connecting rods and crank shaft, you can shorten the cylinder block, then lighten the motor. Engine piston requirements. The piston, moving in the cylinder, allows the compressed gases, the product of fuel combustion, to expand and perform mechanical work. It must be resistant to high temperature, gas pressure, and reliably seal the cylinder bore. Meet the requirements of the friction pair. In order to minimize mechanical losses and wear, experiencing loads from the combustion chamber and reaction from the connecting rod, it must withstand mechanical stress. When reciprocating at high speed, it should load the crank mechanism with inertial forces as little as possible. How they work. Fuel, burning in the space above the piston, releases a huge amount of heat in each cycle of the engine. The temperature of the burnt gases reaches to 1,000 degrees. They will transfer only part of the energy to the moving parts of the motor. Everything else in the form of heat will heat the engine. What remains, together with the exhaust gases, will fly into the pipe. Therefore, if we do not cool the piston, it will melt after a while. This is an important point for understanding the operating conditions of the piston group. Let us repeat the well-known fact: the heat flow is directed from more heated bodies to less heated ones. The most heated is the working fluid, or, in other words, the gases in the combustion chamber. The heat will be transferred to the surrounding air, the coldest one, air. Washing the radiator and engine housing will cool the coolant, cylinder block, and head housing. It remains to find a bridge through which the piston gives off its heat to the block and antifreeze. There are 4 ways. The first path that provides the most flow is piston rings. Moreover, the first ring plays a major role, as it is located closer to the bottom. This is the shortest path to the coolant. Through the cylinder wall, the rings are simultaneously pressed against the piston grooves and the cylinder wall. The rings are simultaneously pressed against the piston grooves and the cylinder wall. They provide more than 50% of the heat flow. The second coolant in the engine is oil. Having access to the most heated places of the engine, oil mist carries away and gives to the oil pan a significant part of the heat from the hottest points. In the case of using oil nozzles that direct the jet to the inner surface of the piston bottom, the share of oil in heat exchange can reach 30 to 40%. But when loading the oil with the function of a coolant, Care must be taken to cool it down, otherwise, overheated oil may lose its properties. Also, the higher the temperature of the oil, the less heat it can carry. Third way. Part of the heat is taken away for heating by the fresh air-fuel mixture that enters the cylinder. The amount of fresh mixture and the amount of heat that will be taken away depends on the operating mode and the degree of throttle opening. But the heat produced by combustion is also proportional to the charge. This cooling path is impulsive, differs in transients, and is highly effective. Heat is removed from the side from which the piston is heated. Attention must be paid to the transfer of heat through the piston rings. If we block this path, then it is unlikely that the engine will withstand long forced modes. The temperature will rise, the piston material will float, and the engine will collapse. Let's think about compression. Let us imagine that the ring does not adhere along its entire length to the wall of the cylinder. Then the burnt gases, breaking through into the gap, will create a barrier that prevents the transfer of heat from the piston through the ring to the cylinder wall. It's like closing a part of the radiator and depriving it of the ability to be cooled by air. The picture is more terrible if the ring does not have close contact with the groove. In places where gases have the opportunity to flow past the ring through the groove, the piston section is deprived of the opportunity to cool. As a result, burnout and chipping of the part adjacent to the leak. From a mechanical point of view, the fewer rings, the better. The narrower they are, the lower the losses in the piston group, with a decrease in their number and height. The conditions for cooling the piston worsen, increasing the thermal resistance of the bottom ring cylinder wall. Therefore, the choice of design is always a compromise.